So thank you everyone. Today I will be covering topic number 2, bridge system and geometry. For this session, I will focus on bridge systems. In the next section next week, the second week, we will have Fernando Sanago from WSP to give us insight on how industry experienced engineer deal with bridge geometry in terms of how to fit within existing roadway. As we know that our plan for topic number 1 and topic number 2 is to be covered in 3 sessions, lecture and a half, and I think we are in right track for that. So today is bridge system and geometry. So here, the focus of this lecture or topic is to start to identify the language in bridge engineering, give the student insight about different terminologies. And this slide is very important slide where we will define different terminologies. For example, what is superstructure, what is substructure, and what is abutment in any mid and short span bridge. In this photo, you will see that these are showing superstructure, and this is showing substructure pier or bend, and this is substructure abutment. If you draw an imaginary line that on top of the bearing that is supporting this part of the structure, whatever above this line of or plane is called superstructure. It includes deck, girders, and soffit. Whatever below this line is considered substructure. It's, if you can see here, we have footing for this frame. This frame, we call it usually bent. So the footing embedded in the soil. We have the footing, we have the column bends, and the columns are joined by beam. We call it bent cap, and this frame is one support of the superstructure. The abutment is to support the bridge at the ends and both ends, and also to provide lateral support to the soil or the earth backfill. So we will discuss more as we go in different part of this abutment, from wing wall to back wall to seat to stem. If we focus about superstructure type for short span and mid span bridges, which is the focus of this class, we can categorize them to 2 categories. One is based on beam bridges or girder bridges. Other category is box bridges. In terms of beam bridges or girder bridges, we have types similar to slab bridge, T-beam bridge, precast concrete girders, composite weld steel girders. For box bridges, you have reinforced concrete R/C box girder. It can be cast in place, or sometimes it can be segmental box girders. We have B/S, which can be also cast in place or with external pre-stress as segmental box girder. We also have composite structure steel box. And we will, during the following slide, elaborate on each type. For beam bridges, the first type we will talk about today is slab type. Your riding surface, or the structure system that supports your riding surface, is made of a slab. It's very economical for span below 40 feet. The detailing of the formwork is very simple because all you need is to form the side and the bottom of the slab to support the reinforcement and the concrete during casting. Appearance looks neat and simple for short span bridges. Structure-wise, in design, it's a standard design. You don't need to do stress analysis except for non-structural span layout. If you have, for example, some curvatures or really bad skew. And we covered that in the last lecture when we have the difference between skewed bridges and curved bridges and steel and straight bridges. In the second type, which is T-beam bridges, is actually suitable for a span between 40 feet and 60 feet. You have to form a drop beam and you'll have a slab on top, and they act monolithically, they cast monolithically. So it's called T-beam because if you take a section between the two spaces, it is actually a T-beam. For construction, formwork is complicated than the slab bridge because you have to form all sides of the beams. And it's very also complicated if you have a skew. In terms of appearance, it is not desirable when you drive below it. And one thing important here we need to emphasize on that the depth to span ratio, the depth of the T-beam to the span ratio, it should be as minimum of 0.07 for simple spans and 0.065 for continuous spans. And we will cover that in each system. What is the minimum depth to span ratio? In terms of the second system called precast, pre-stressed girder, most likely to be pre-tension, meaning that you will have to use pre-stressing, but you tension, for example, if you have a wall, rigid wall here and rigid wall here, and you stress your strand under tension across the wall, and you cast your girder, and after girder, after 7 days in curing, you cut the strand, so the tensile force and the strand need to go to the original position, impose compression on the girder, enhance stresses in tensile zone when you load it. It's more cost more if you compare it to RC for the same depth because of the use of pre-stressing. It is done in fabrication plants and require really careful handling after fabrication because the pre-stressed is acting in one axis, which is a strong axis. If you tilt it, it will act on a weak axis, and it may actually cause failure during handling and placement. It appears similar to the T-beams. It's suitable for a span between 30 and 150 feet. Usually we don't do around 30, so we can start at 70, 80 feet. There is standard girder types, which is called ASH2, and also it varies between a state and another. Usually we are limited to 120 because of hauling over state highways. However, myself, I was able to design one bridge with span up to 165 feet. The depth to span ratio in this case, this is a depth, and this is maybe the span ratio. It should be for simple span is 0.045 and for continuous span 0.04. And this is showing of the one image showing the craning of one girder, and you can see here one girder already set up, and this image is showing every line of girder already set up, and as you can see for the other span it will continue over the bearing, and they're going to be forming the bottom of the slab and placing reinforcement to cast concrete to achieve composite action between the slab or the deck and the pre-stressed girders. The next very famous system is composite steel I-girder bridge. As you can see here, I'm very sure that you are familiar with that. If you drive around New Jersey, New York, even Miami in downtown, you will see those kind of systems where you use built-up sections, steel built-up sections, suitable for a span between 60 and 300. Construction details and formwork is kind of simple in this case, and you can transport 120 to 150, but you can go up spans 300 because you have advantages of splicing those girders. Structure-wise, it's a low dead load compared to concrete because the girders in concrete in much bigger areas. Even the unit weight is less, maybe by a third, but the area is much bigger. So if you have a poor soil, this structure will provide light structure compared to concrete. The span to depth ratio is, in this case, for simple span 0.04, for continuous span 0.032. The same information is presented here, but one additional photo you can see here. We usually, during construction, when you place the girder, you have to brace them together. The reason is to provide lateral support and stability to the girder to prevent the girder from failing during construction under lateral loads such as winds. Those girders sometimes in larger span reach to 7 or 8 feet depth and provide large area for wind loading that can overturn this girder. So you always have to use those bracing to connect girders together. And also during the service life of the bridge, or the life of the bridge, it actually helps the girders to work together as one structure for the turning moment or forces. If you, for example, if the truck loading is concentrated in one side, it may provide overturning, so you need the superstructures to act as one unit and distribute the load rather than loading just the girder that underneath the truck. The second category we discuss is box girder, and in this case you have reinforced concrete cast in place box girders. And it's very important to understand this sketch. The top slab called deck, the bottom slab called soffit, and you have also girders. So you form by this shape a box, several cells in a box. So it's actually very suitable for span from 50 to 120. It's only rectangular, reinforced concrete. Construction formwork is simpler than the T because you have bottom slab, top slab. Appearance looks good from all directions, and can also, those cells can be used as utility lines. The depth to span ratio is 0.06 for simple span and 0.055 for continuous span. Those kind of box structure, if you know a little bit about torsion stresses, always torsion stresses for section that has boxes is bigger than the T-girders shapes. So if you have curved alignment, and you will have most likely huge torsion effect, box girders can be the better option. Here is the same slide, but here showing the formwork for the cast in place. You form the box, and sometimes you also, the beam that we mentioned, the cap beam earlier, also can be cast as integral. The second type of boxes is pre-stressed cast in place box girder bridges. And in this case, you can see the reinforcement is placed And those ducts are to create a void after casting, so you can insert pre-stressing strand and post-tension the girder after. So you cast first and post-tension second, or tension second, and release the force to apply those compression forces. Same as conventional box girder in terms of constructability, except if you have to be careful with the profile of the ducts and a lot of quality assurance for that. It actually looks better than conventional in terms of appearance. Spans to depth to span ratio for simply supported 0.045, for continuous support 0.04. As we mentioned before, it's also very good for torsional resistance. And here is one photo showing after casting the box, here where we insert the pre-stressing strand and post-tension the structure after. The last box girder system is composite structure steel box girder, as you can see here. So the box is formed by steel sheet. They are welded together. Cost is expensive compared to I-girder, but it can go up to 500 feet. It need really skilled labor and controlled environment for detailing and welding. It goes span up to 200 feet with multiple box. And also the depth to span ratio is 0.04 for simply supported and 0.032 as minimum for continuous spans. Here is a close up photo for how it looks like. So you have steel top flange, you welded with one web, bottom flange is wide, you have also two other top flanges and webs. So in this case you have three webs, and they are all welded together. And after that you have what we'll discuss later, shear studs, and those shear studs with the slab are provided to provide actually composite action between the girder and concrete. So also after that you form the slab for the slab, and you have overhang, and you place your reinforcement longitudinal and transverse, and you cast concrete. You create composite structure steel box girder. This is actually where we can see from AASHTO. So AASHTO LRFD, you will be able to see that in table 2.5.3.2.6.3-1 is the minimum depth requirement for each superstructure type based on material. First one is reinforced concrete, second one is prestressed concrete, third one is steel. If you can see here that, let's say I want to check the minimum depth of T-beam made of reinforced concrete. You go in this line, you select, you get 0.07 and 0.065 time the span to get your minimum depths, including the. Let's say for steel, for prestressed concrete precast I-girder, it is same case, and you can go back and check the other slide, and they are matching. And here, what you can see is two different numbers for overall depth of composite I-beam, or depth of I-beam portion of the composite. Typically, your girder as composite is made of two flange and web, bottom flange and top flange, as you can see, and you have this inclined thing for hunch, and you have the slab. So the first depth H1 is the depth from the top concrete to the bottom steel flange. You can call this H1. So when you check H1, you have to use 0.04 L for simply supported, or 0.032 for continuous support, continuous span. And if you want to check only the depth of the portion of the steel, you have to check H2, which in this case, this is H2, 0.03L or 0.027L. Sorry, maybe my video is not showing all the numbers, but you have the slide and you can check that too. Superstructure type for short and mid-span, and this is a terminology, just a reminder, because you always have superstructure, substructure, abutment. In this slide, there is a mistake. You have to remove the superstructure and use sub, because we are actually talking about substructures. Here we will focus about bends and piers. So the bends, as we discussed, having footing embedded in the soil or earth. We have the columns, we called it column for the bend or column bend, and we have bend cap, which is the beam that connect all the bends. The beams can be called what's called drop cap or integral cap. Also, the foundation system can have piles, group piles or single piles, pile shaft, and this is what we will be covering in next slides. In terms of substructure bridge bend, you have two systems. The first one is drop bend, and from the name it's clear that you have the superstructure girders seating on bearing on top of your girder. So the girder is dropped from the superstructure. The second type is integral bend, where you can see here, this is a line of the beam that is actually integral with the slab. So it's cast monolithically with the superstructure. The piers are referred to the wall type substructures. So you have continuous support in some cases. And the abutment, as you can see here, here is your abutment, which is a C type. So this C type abutment, your superstructure comes and sits on the seat, and this is the stem side, and this is the back wall side, and there is one wall from this side. Your foundation can vary from shallow foundation to deep foundation, and you also have what's called this concrete approach slab. There is another type for abutment called diaphragm abutment, which you cast the diaphragm and the end of your superstructure monolithically, can be supported over pile or supported over split footing. So generally speaking, bridge type selection, you should all satisfy local need, means that when you build your bridge in a certain state, you have to follow the need for trucks. So trucks differ from a special permit truck, not a design truck, as we can discuss later during the loading, differ from state to another. So you have to follow this and satisfy local needs. Girder types differ. Environmental conditions differ. So you have to follow local need. You cannot design a bridge with California specification thinking it will fulfill requirement of Florida. You cannot do it from New Jersey thinking it will fit requirement of Texas. And this is what will happen during our semester-long project, that you will be asked to design some bridges in different states. Most appropriate bridge systems should be selected from local available technology. In the last slide or last topic, we showed a big emphasis on accelerated bridge construction as construction technique, from prefabrication to bridge slide to actually SPMTs. But if you don't have those technology within your state, plus you don't have experience from contractor, you should not import it from other state, because it will be much expensive and make a case problem. But this is not actually to hinder the implementation of those technology, but it can be built in a pilot scale, but in general, you should use local available technology. In general, posts pre-stressed box girder, in case post tension, is very common in the West Coast, especially California, and structure steel built girder and pre-stressed eye girder is very common in East Coast and South region of US. In terms of structure system, which gonna be the focus of the following few slides, we need to know how to frame those structures. So we have superstructure, substructure, and abutment, and how to do the boundary condition. For example, this slide is repeating again and again just to make sure that every student knows the language that we speak on bridge engineering in terms of superstructure, substructure, abutment, stem, wing wall, etc. So we covered the cast in place box girder system, and we also mentioned about the soffit bottom slab, the deck, and the girders. And you can see here those opening called cells, the top slab called deck, right? The bottom slab called soffit, and the girders are called either interior or exterior girders. And you may have overhang and railing systems. As you can see here, close up, these are the cells. There is bridge overhang, there is deck, soffit, interior girder, and exterior girders. You need to go back to the famous table. You need to design those bridges and make sure that you actually using minimum depth. And this table is actually to kinda ensure a right deformation or deflection. So in terms of box girder for reinforced concrete, your minimum depth should be 0.06. The span length, if you are simple spans, if continuous span, you use 0.055 times the span length to get your minimum depth. Some information about how to size it. Let's say you have a box girder that the roadway width is around 48 feet. So what you usually do, you need to make sure that you already get the minimum depth or the depth that you choose for your girder, right, which is this dimension. You have to size your structure. So the girder spacing, which is the distance from the center of the girder to the center of the other girder, this S, has to be as starting point 1.5 the depth. So you have kind of rectangular shape, not a square. The maximum, make sure the maximum S value is 14 feet. The thickness of the top slab or the thickness should be taken as the spacing S over 40 from the first step S, and the minimum thickness that you can use is 7.5 inches. The soffit has to be at least the spacing between the girder over 17 with minimum of 6.5 inches. For the overhang usually is made of a slope, so it's a deeper in the exterior girder and shallower in the tip. So if you want to size it, the overhang should not go more than 6 feet and 6 inches, as you can see here. The depth at the tip should be 7.5 at least, and an exterior girder. This is the exterior girder. The depth here should be at least 12 inches, 1 foot. And the girder thicknesses, which is exterior or interior, can range from 12 to 18 inches. Also, remember that to make it looks and appearance better, sometimes the exterior girders are made on a slope. So you will have the first girder in a slope, and the slope actually is preferable to be 1 horizontal to 3 vertical. Moving forward, in order to put the structure system, if it is a beam or what kind of boundary condition or framing system, you know that you have the load from the top slab, soffit, all the diaphragms, which is here the end diaphragm is casting, here you have a hole, but at the end you have to have diaphragm, some wearing surfaces, your diaphragm and elastomeric bearing. So if you have the support, as you can see here, simply supported, you just have a system, looks like a simply supported beam to carry the gravity loads. In lateral loads such as wind, especially seismic, what we build off, we build this side, and the side we call it shear key. So when the load hits, it's support to a certain level and fuse after that. So this is the way that your system has to be, because you cannot allow the system to slide. So the system will have in the lateral dimension or transverse direction those kind of supports. This multi-span bridges for box girder, you can see it from an actual bridge, that they usually are very nice if you have curvature because of the torsion capability and resistance. And those type of the bridges can go up to from 400 to 600. You make sure that when you frame your structure as possible, you can have your first span actually is 3/4 of the interior span, because you know very well when you have a continuous span, when you draw your moment diagram, you left WL square over 8 from higher points, while if for first span you left from the midpoint, because the first span is almost 0. So usually if you use equal spans, you'll have higher moment here than this point. So to make them kind of equal, you make you shorten the span, then the interior spans, to reduce your moments, to make it closer to the interior span, so you get economical design. In this case, we have the integral bend cap in this connection. When we have seating here and seating there, so the seating will provide hinge and roller. However, because this is built monolithically, this will be a frame that you need to solve to carry the vertical loads. And here is one illustration on how this integral abutment is built, integral bend cap is built with a formwork. So when you cast, you actually build a solid girder here, which is also act as a diaphragm. In the substructure wise, you may have one single column or double columns bent or more, or multi-column bends. For a superstructure with less than 45, you can use just one single column. This column can be supported over bend cap, pile cap, and group pile. Or your second option will be pile shaft, where the column continues into the soil to act as a pile. There is also type 2 pile shaft, when you actually enlarge the pile diameter to be bigger than the column diameter. This is actually very important, because in seismic zone, you push the damage to happen in area that you can investigate. In more than 45 feet, you will have to use more than one column, in this case 2 columns, so the spacing between the columns and the overhang, the ratio should be at least 0.4. This overhang should be 0.4 s. And for steel blade girder, which is going to be the topic of topic 6 for us in this class, you will have a slab that act composite with the girders. You will have steel blade girders, which as you can see here. You will have the cross frame, as we discussed, to make stability during construction, and also make the entire girder system to act girders. And also these are supported over the spearing. And if you can see here, sorry again, because it's actually covered by my video, but you can go back to your slide. Here you can see the overall depth, which we discussed earlier, or the depth of only the eye girders. As you can see here, I extracted for single span is 0.04 for the overall depth and 0.03 for continuous. You can space your girders at ring between 7 and 15. I personally like between 8 and 12, and you can use it by this rule: 1.5 the depth, overhang, similar rules as the cast in place box girder, and also thicknesses are similar to cast in place box girders. And here I'm concluding my presentation for the first part, which is bridge systems. And I'm looking forward to have you in person with us. Our industry partner, Fernando Sanago from WSP, will cover the second part of this topic, which is geometry, which is very important, how to tie the bridge system to the existing roadway for better riding surfaces. With that, look forward to see you in our next presentations.